Welcome to everyone. This activity is the result of a collaboration between Garrett Motion and POWERTECH Engineering. It is about the numerical assessment of adaptive ECMS strategies for a gasoline hybrid electric vehicle on type approval and RDE driving cycles. This is the agenda of the presentation. After a brief introduction about the aim of the work, I will move to the case study chosen. I will then explain the reason behind the adoption of adaptive energy management strategy and the ones investigated in this work. I will then bring you to the results and finally I will sum up my conclusions. The need to decarbonize transports and the need to reduce time and cost of the development process of electrified vehicles can be tackled by numerical simulation, which is the elective ground for the development of complex and innovative energy management strategy. The aim of this work is to develop an energy management system that adapts its operation in real time and that can guarantee charge-sustaining operation and optimal control on type approval and RDE driving cycles. Concerning the case study, for this work we choose a hybrid vehicle powered by a gasoline engine with 172 kilowatts and a 30 kilowatts electric motor, placed between the engine and the P2 transmission, the so-called P2 hybrid. The vehicle is a mid-size SUV featuring a 6-gears transmission. The entire vehicle is modeled in GT Suite with a map-based approach for the powertrain, the internal combustion engine and the electric motor, and an equivalent electric circuit represent the battery pack. The energy management controller of hybrid electric vehicles is based on a supervisory controller which defines hybrid electric vehicle mode or regenerative braking operations and the proper energy management strategy that determines the power split between the internal combustion engine and the electric motor. Among the various energy management strategies, the ECMS, the equivalent consumption minimization strategy, is chosen in this work because of its industrial appeal and ease of calibration. In the ECMS approach, instant by instant, this cost function, representative of the equivalent fuel consumption, is minimized. This cost function represents the sum of the engine fuel consumption and a fictitious virtual fuel consumption associated to the power coming from the battery, based on the assumption that the energy stored in the battery must be replenished using fuel energy. The parameter used to convert battery energy into fuel energy is the so-called equivalence factor K. In this work, a map-based power split optimization was used. An offline optimization tool was used to generate power split maps as a function of driver power, total power demand, driveline speed, and equivalence factor, taking into account e-motor, internal combustion engine, and battery limitations. The equivalence factor is the key of the ECMS. It is a synthetic value that is used to estimate the average chemical to electric conversion efficiency. It is a representative of past, present and future efficiency and affects charge sustainability and the effectiveness of the strategy. It is usually calibrated for a specific vehicle architecture and mission profile to guarantee charge sustaining operation. A fixed equivalent factor guarantees charge sustaining operation and close to optimal results in type approval tests, as seen, for example, on the NDC presented in the left figure. However, on long and high varying load mission profiles, the ones presented on the right of this slide, a single K may produce imbalance in the SOC profile, which is depicted in blue, jeopardizing the advantages of a hybrid architecture. In order to overcome these limits, different adaptive ECMS techniques are proposed. Concerning the main adoption techniques, in this slide I reported three most significant adaptive ECMS methods, which are aimed at operating the vehicle in charge sustaining. The first set of methods is based on the feedback from the battery state of charge. The actual battery state of charge is compared to a target value, and a proportional or integral controller acts on the equivalence factor K to adjust during driving phases the power split in order to achieve the target state of charge at the end of the cycle. Another method is based on a driving pattern recognition approach. During driving phases, the emission profile is acknowledged, and the proper K factor, the one which guarantees charge sustaining operation, and so the optimal power split, is chosen. Finally, also driving pattern prediction methods can be adopted. They differ from driving pattern recognition since they are aimed to preliminarily predict a certain emission profile or driving pattern and behave in a proper way with respect to driving pattern recognition techniques. For the sake of brevity, in this presentation I will show you only the results of the first two methods. Concerning the first method, a so-called autoregressive moving average filter has been developed and integrated in the GT model based on the following formula, which accounts for previous equivalence factor and instantaneous battery state of charge. We see that for at each update interval t, the equivalence factor k is updated as a function of the difference between the target state of charge and the actual state of charge of the battery. This is a so-called proportional term. Additionally, a memory term accounts for previous states of the equivalence factor. The equivalence factor computed with this relation is directly used as input for the choice of the power split map. This controller is entirely developed in GT Suite. The second approach is based on the driving pattern recognition and was developed in Simulink and integrated in the GT Suite model with a Simulink harness. In this slide, the development of the controller is shown. First, 20 type approval driving cycles are chosen, and for each of them, the charge sustaining equivalence factor K is assessed. Then, a statistical analysis of 18 driving metrics, as for example the mean run velocity, the maximum acceleration, the cruise fraction, and so on, is performed for each driving cycle. Then, a principal component analysis is used to reduce the numerosity of the data, and the driving cycles are grouped in 5 different clusters, representing, for example, urban, extra-urban, or highway driving style. Finally, the average equivalence factor of the driving cycles belonging to a certain cluster is defined as the charge sustaining K equivalence factor for a given driving pattern. During vehicle operation, these driving metrics, the vehicle velocity of the last 200 seconds are instant by instant computed. Average run velocity and the other metrics are transformed on PCA coordinates, and after the identification of the closest cluster, for example in this slide we see the third one, the driving pattern is recognized. Then the equivalence factor of this driving pattern is used to select the consistent ECMS map. Moving to the results section, the adaptive techniques developed so far are tested for 3 different cases. A reference vehicle with a fixed equivalence factor ECMS is depicted in blue. Then we have a case A, which adopts the adaptive ECMS based on the state of charge feedback. And finally, in green, the case B, which is the adaptive ECMS based on the driving pattern recognition. The tests have been performed along different driving cycles, type approval and RDE, but in this work we will see only the results on the NADC and 2 different real driving emissions tests, RDE and city-to-city driving cycle. In this slide, the results along the NADC driving cycle are reported. The reference vehicle featuring the ECMS with fixed K is depicted in blue. On the left, the performance of the adaptive technique adjusting the K factor on the basis of the state of charge feedback. The results are reported in red. While on the right, we see the performance of the adaptive techniques based on driving pattern recognition, which is depicted in green. The upper figure reports the state of charge along the cycle, and in the lower figure, the value of the equivalence factor is shown. The K factor of the reference case is calibrated to guarantee charge sustaining operation. In this case, with fixed K, there is no great impact on charge sustainability since the NEDC is quite short and a single K is enough to guarantee close to optimal power split. Using the state of charge feedback, the state of charge is maintained between 0.4 and 0.6. If we look at the results on the driving pattern recognition, we see in the upper part of the right part of this slide that the driving pattern recognition technique recognizes two different patterns, the urban and the extra-urban pattern along this cycle. However, also in this case, the state of charge is stable and between 0.4 and 0.5. In this slide, the results along the RDE driving cycles are presented. In this case, a single K is not enough to exploit the battery during the main part of the RDE, hindering significantly the regenerative braking capability, since the battery is full for the great majority of the time. With adaptive ECMS with the state of charge feedback, we can instead maintain the battery state of charge between 0.4 and 0.6. With DPR, the oscillation is slightly larger, especially in the last part of the cycle, but the state of charge is between 0.3 and 0.7. Finally, we see in this slide the results along the city-to-city driving cycle, which is mainly an highway driving cycle followed by a urban driving cycle. Also in this case, a fixed state of charge would deplete the battery pack just after 400 seconds. Thanks to the adaptive ECMS, the battery state of charge stays between 0.4 and 0.6. With DPR ECMS, the battery state of charge stays between 0.2 and 0.8, which is better than the reference case, but this shows that some driving cycles may be mission critical for the management of the battery with these adaptive technique. But we have to keep in mind that the controller memory is based on type approval driving cycles, and some RDE driving cycles may have driving matrix far from the ones used for the development of the driving pattern recognition. Here the full consumption results are reported along the 3 driving cycles analyzed. The adoption of adaptive ECMS techniques has a limited impact on NEDC, since it's very short, while on RDE, the adaptive ECMS techniques has a significant impact. The adaptive based on SOC feedback improves CO2 emissions by 4 grams of CO2 per kilometers, and using the driving pattern recognition, we are able to achieve an improvement up to 6 grams of CO2 per kilometer, thanks to the optimal management of regenerative braking and the power split. Finally, along a city-to-city driving cycle, we do not see much benefit other than the improvement in terms of battery state of charge operation, which is controlled and between an acceptable state of charge swing range. It is to be said that this driving cycle is mainly an highway driving cycle with limited regenerative braking and high power operation, and for these reasons, the internal combustion engine is mainly switched on. To conclude, an improved energy management controller was introduced into an existing GD power vehicle model, representative of a P2 mid-size SUV with a gasoline engine and an electric motor. 2 auto-adaptive energy management controllers were developed and integrated in the vehicle model. The first one based on the state of charge feedback, and the second one based on a driving pattern recognition approach. These two adaptive ECMS techniques have been tested along type approval and RDE driving cycles and compared with the reference vehicle featuring an ECMS with fixed K. An improvement up to 6 grams per kilometers have been achieved along an RDE driving cycle, demonstrating the impact of this energy management strategy that can guarantee charge sustaining operation. In particular, the benefit coming from a driving pattern recognition approach able to instantly determine optimal control was shown. This project highlighted how virtual plant can be adapted for the development of advanced energy management controllers for hybrid electric vehicles. Future developments of this work will involve the improvement of the charge sustainability of the DPR ECMS to reduce state of charge swing and so battery aging phenomena by expanding pattern recognition capabilities to RDE driving cycles, and also the development of a controller, improved controller based on concurrent DPR and feedback from the state of charge. I would like to acknowledge my co-authors, Emanuele from POWERTECH, Philippe, Adam and Sujit from Garrett Motion. Thank you for your interest and I am open to your questions.